In this video, I'm going to explain how to set up a welding simulation of a pipeline, a simulation that predicts the phase fractions and hardness around the weld. I'm going to need 3 programs. So first we have Abacus open. Second, we have a command prompt in Windows or terminal if you use Mac or Linux. But should have the Abacus command available. And finally, we have a text editor. I have Visual Studio, but you can use any text editor, of course, open in our working directory. So in Abacus, I've already drawn the weld. You can see over here. Create a part over here. First draw the outline. Let me show you this. So actually what I have done over here is I've used an image of an actual weld to draw this offline. I can show you that. Need to play around a little bit with these values, but if you find the right ones, you can actually see that we have an image of the weld overlaid of our sketch over here. So we've drawn our weld based on this image, and we have divided our weld into sections, which you can usually do with partition phase over here, and show you the partition. We basically have 2 weld beads over here, and some partitions for meshing. Next, we go to property, and we can define materials. Let's create a material. Let's actually create 2 materials. So one for the base metal and one for the weld metal, so that we can later set different chemical compositions for either a base or weld metal. So let's name this one base. And the material behaviors that we need to define are a density, and that one needs to be set to 1. Actually, the simulation code handles the density internally. That's why we need to always set it to 1 over here. Then we need to have a user material of type thermal. We need to have depth var, which are solution dependent state variables, and we need to have 12 of those. And then finally we need to set user defined fields. Okay, that's for one material. Now let's create, copy this material. Actually, sometimes my windows do a little bit weird and they disappear. But let's copy that material to weld and name it weld. So now we should have 2 materials with the same properties. And then we need to assign these materials to sections. So let's create a section. Let's create a base section, the base material, and let's also create a weld section with the weld material. And then finally we need to assign these sections. So base, the base section, and to the weld region, the weld section. Our next step is to go to property. I'm going to create new materials. Let's create 2 materials so we can assign different properties to them. Let's call the first one base material. What kind of the material behaviors that we need are the density, which needs to be set to 1. The density is actually handled by the user subroutine itself. That's why we need to set this to 1. We need a user material with user material type thermal. We need state variables, 12 in this case, and we need to give material behavior, expansion, and use a user subroutine uexpand. I guess let's create a second material for the weld in case we want different properties to use for the weld. So let's copy this material. I know somehow my windows get messed up, but they disappear sometimes. And let's call it weld. So now we have two material properties over there. Then we also need to create the sections of our geometry that we're going to assign the material properties to. Let's create the first section. Let's call it base. Select the base material. And let's also create a section for the weld. And select the weld material. And then we need to assign these sections, which you can do over here. So let's first assign the base material, base section, and also do the same thing for the weld. The next item in our module list is assembly. Just need to create an instance of the part that we have created. Then we're gonna create the simulation steps. The first step we always need to start with, create a step, is a initial step. This step is needed to initialize some variables and the subroutines. We need to have a heat transfer step over here. Okay. And let's give this, can just be a very small time period, and incrementation can be done in one step. It's fine. And you always need to give in a maximum. Oh wait, put this to fixed. Then let's create an actual weld pass. So we have two weld passes. And each weld pass is going to consist of 3 steps. First, I'm going to have a heating step. Let's call this heating 1, which is also a heat transfer step. Gonna heat this up over a time period of 3 seconds. Here we're going to use automatic incrementation, maybe 100 time increments initially, and it is allowed to go smaller. Okay, after the heating step, we're gonna need a step where the weld bead is inserted, and because material is inserted, we again need to initialize some variables in our subroutine. So we're gonna have insert step, which again can be a very small time increment. So let's set this to fixed again. Oh, this is not, that's very large, of course. Like this. Yep. Yeah, that's also, this is also small. Okay, that's better. And then as the final step of the weld bead is of a weld pause, is letting it cool down. And now let's give a cooldown period of 2 minutes before the next weld pause is going to take place. Again, let's use a minimal of 100 increments over here. This one I usually put very low, a little bit higher, and like this. So that's for the first weld beat, and we need to insert a second weld beat. So we're gonna create the same 3 steps again. But now for the second weld beat. The insert step. And our last step, just the cool down step of the second weld beat. And this one we can probably let it cool down for 10 minutes. Let's use, let's see. Let me check what kind of stuff we used here. Okay, 1.2 initial. Might be a little bit too high, but we're gonna okay. After I tried to run the simulation, turned out I need to make 2 small changes in the steps. In both cooldown steps, the initial step size needs to be much smaller, more like 1.2 times 10 to the power minus 4. That is because in the cooldown step, the temperature goes down quite quickly in the beginning, which is much more than this 50 degrees per increment. So either we need to increase this one or decrease the step size bit. And this works good for the settings. I forgot it now. And we will do the same thing in the cooldown step. Just going from top to bottom in the module list, go to interaction. So what we need to do here is actually deactivate and activate the weld passes again at the right moment. So let's create a first interaction. Let's call this weld beat 1. In our initial step, model change, we can select a region over here. So let's select weld 1 and we choose deactivate in this step. You can now see our interaction over there. Let's create another interaction, call it weld E2, which we also want to deactivate in the first step. So select region weld 2, deactivate in this step. Okay, and then we actually want to make sure that they get reactivated at the right time. So two ways you can do that. One is to states over here. So the first weld bead we want to have activated again in step 3 over here, insert 1. So in a model tree we can click on reactivate in this step. Another option is go here, right click on interactions, go to manager, and you can actually see all the weld beads. And weld bead 2 we want to reactivate in step 6 over there. So you can edit this one, reactivate in this step. Okay. To model the heat loss to the environment, we also need to create interactions. We can take into account convection or radiation. Let's first set up the convection boundary conditions. So let's create an interaction. Let's call this convection, and this is for the first heating step. So heating 1. There needs to be a surface film condition, and now we need to select the surface. We want to select some internal surfaces because some parts, some regions of our geometry are going to be deactivated in this step. So usually in Abacus now I can't select an initial surface, but if I do click on their surfaces, then again selecting viewpoint, now usually I can select these surfaces over there. So the top weld bead is first going to be inserted, which means that we're going to have heating along these. This makes it easier to see. So we're going to have heating over these surfaces, which means that we need to have heat loss on this surface and on that surface, and then furthermore selecting all the outer surfaces there and on the entire pipeline. Let's call this also surface of heating 1. Okay. Then it asks to what is the outer side of the edges, which doesn't matter for heat loss space. It's not a vector, but well, yellow in this case. And then we need a film coefficient for air 2.5 times 10 to the power minus 5. Seems to be a reasonable value for air, and the sink temperature of 20 degrees. This needs to be instantaneous. Okay. We also need this convection, similar convection for boundary condition in the cooling down step. Cooling down 1. In the cooling down step, this part is inserted, so we need to select again this surface. Let's call it surface cool down 1. It's yellow. Let's insert the same values. 20. Then create a boundary condition for the heating 2-step. Let me see, in heating 2-step, this side's gonna be heated up. So we have heat loss there. That. Surface heating 2. Minus 5, 20. Okay. And the final one, the last cool down step. So it's convection cool down 2 over there. And now both well beads are inserted. So this is just the outer surface. Cool down 2. And 20 degrees. Okay. So to create the radiation loss to the environment, you also need to create an interaction. Let's start again for heating 1. So let's call this radiation heating 1, which is a surface radiation. Now, because we have already created these surfaces, we can just choose heating 1 over there. An emissivity of 0.8 seems reasonable here. Ambient temperature of 20 again. Okay. And well, let's repeat that for all our steps. So radiation cool down 1. Select the appropriate surface. 0.8, 20. Okay. Heating 2. And the final one, which is cool down 2. Okay, so to check if we implemented everything in the right step and to deactivate everything in the right step, we go to the interactions manager over here. So let's see, we have our, for convection, created the heating 1 step in the heating 1 boundary condition in the heating 1 step, and we want to deactivate it here for the convection in the cool down one. This one created in the right step, and we want to deactivate it here. We only want these to be active in the road step. And then if here this one also correct, deactivate, and do the same thing for the radiation boundary condition. Deactivate. Okay, so now everything is created and deactivated, all the boundary conditions in the correct steps. Then the boundary conditions. So we go to load over here, the temperature boundary conditions, that is. We can create a boundary condition. Let's call this one heating 1. In the heating 1 step, so what we want to do is we want to increase the boundary condition on the edges of the weld bead that's going to be inserted. So let's create a temperature boundary condition, and we can choose it here. Let's call this set heating 1. Okay. And I want to actually have this magnitude to 1500, 1500 degrees. And what we actually want to do is we want to not, okay, so we don't want to have this instantaneous, but we want to ramp this linearly over the time step. But let's insert it for now. So the trick to do that is to go back to steps, and we should have put here default load variation with time to ramp linearly over step. Okay, and do the same thing for heating 2, ramp linearly over time. In the other steps we don't apply boundary conditions, so it doesn't matter what we put over there. Now let's check only that this one, okay, yeah, so this one is now also set to ramp, but what we want to do over here is create an amplitude. Let's call that const an amplitude of 1. So it basically means that if we now select that amplitude, that gets multiplied by this. So for constant, this one is immediately constant. And we need to do the same things in our heating 2 boundary conditions, because this one needs to be constant. And here also const. Okay, now let's go back to our boundary conditions. Heating 1 over here, and this one is now set to ramp, which basically means that it starts out at its initial temperature at 20, and then in the time step linearly goes to 150 degrees, 1500 degrees. And let me see if we can go to manager over here, and we want to actually deactivate this boundary condition after this time step, because otherwise it will keep it at 1500 degrees. So let's deactivate this one there, and let's create the heating 2 boundary condition 2, which select the right surface, heating 2, done. 1500. Okay, let's go to our manager again. So this one's created in the heating step and deactivate afterwards, like this. Next, we want to set some initial values that we can do in predefined fields over there. So here you can create predefined fields. We always want to do this in the initial step. And let's start with the temperature. So we want to have a temperature, and we're going to have a temperature of the base metal. So let's call this temperature base. And we can select the base metal. It's gonna start up at 20 degrees. And we're gonna create a temperature, initial temperature for the weld metal. And that one, actually, this one, so the weld metal is gonna be inserted, and it's gonna be inserted at a temperature of 1500 degrees Celsius. Over there. So we have now created two temperature fields. And you can actually see if I select them that there are some nodes on the boundary which are part of both predefined fields over here, so of the weld and of the base metal. And the way Abacus handles those, it gives the initial values of the field which is located the lowest in the tree over here. So in this case, that's the weld. But we do not want that. We want to actually have these nodes initially the temperature of the base metal, because the weld's not going to be there yet. So you want to change the order in the tree over there, and a workaround trick to do that is to basically put a number in front of the name. So let's put a 2 in the name over there. There, temperature 2. And this one, you can see that they've already shifted around now. Let's give this one on temperature 1. Okay. We also want to set some initial values of some fields that are going to be used in the user subroutine. Let me open the text editor and the user subroutine that we're going to use. On the top over here, you can see the fields that it uses and the numbers associated with it. So we have 5 phase fractions, XF standing for phase fraction of ferrite, pearlite, bainite, martensite, and austenite. We have grain size, and we have our hardness prediction. So it's going to be placed in hardness prediction is going to be placed in field 7. What we want to assign is probably a ferrite pearlite microstructure in the base metal initially. So let's create a predefined field. Initial step, and let's call that fraction ferrite. I'm gonna choose field over there. Continue. Let's select the base metal. And the ferrite was field variable number 1. So this one over here. Let's set this to magnitude 1. And we're gonna create the same thing for pearlite. So we have a fraction pearlite. In the initial step, the base metal pearlite was field variable number 2. And let's also set this magnitude to 1. For ferrite and perlite, you can both set them to 1, because based on the chemical composition, it calculates an equilibrium fractions between those two, and then automatically resets them to those. So you can just use 1 here if you want a perlite microstructure, like this. In the weld metal, we want to have an austenite initially. It's inserted, and it's inserted at 1500 degrees Celsius. So you want to have an austenite phase fraction initially. You can do that in the same way as a ferrite and perlite, but you don't actually have to do that, because if no phase fraction is set, it's basically the remainder of phase fraction that is left. So 100% in this case is set to austenite. We do want to create some predefined fields for the grain size and maybe for the hardness. The hardness is not definitely necessary, but to get nice images and in regions where basically the temperature does not reach the austenization temperature, this hardness is always maintained. So to compare with experimental images, you can set the hardness. Let's first set the grain size, which was G size, field the base metal, and the grain size was field number 6. So let's use 6 over there. Let's set this equal to a grain size of 30 microns. And we actually also want to set a grain size in the weld metal, which is much higher because it's inserted at a high temperature than the grain size in the base metal. So we should have named this one grain size 2 base. And let's create a field, grain size 1 weld. For the weld metal, field variable number 6. And let's give this an average grain size of 100 micron. And then finally, we want to set the hardness. Which was 7. We could just set this in the base material. It only matters for the regions that are not going to be heated sufficiently. So 7, let's set this for E1 equal to 160 Vickers. Okay, that were the initial fields. We still need to mesh the geometry, so you can do that, module selector over there. Let's go to mesh, and you can see the edges if we want to have some control over the mesh size in certain regions. So let's see the edges. I have created this set over here, which are the edges of the pipeline, and let's give it a quite coarse seed of 2 should be okay over there. And then also select this set, which are the edges in the weld region. See it better like this. And let's give that a smaller mesh size. Let's say 0.2. Okay. And let's give some global seeds. And in the global seeds, you need to set a minimum size control. You need to make sure that it is equal or lower to the smallest seeds that we have done, so 0.2 in this case. Okay, that's the seeds. You should be able to mesh this now, but let's check some mesh settings. Go to controls over there. Basically select the whole pipeline. Done. We want to make sure that this is put to quad, so we use quad elements. And then next the element type, you can select all regions over there, and we want to use element type heat transfer of quadratic order over there. So this is okay. Dismiss. And now we can mesh our geometry. It's okay to mesh the parts. Okay, you can see we've created a mesh, which in the pipeline is relatively coarse. If we zoom in, it is finer in the weld region. Then one final thing we still have to do in a thermal model is set the model attributes. So let's go to here, model attributes. We need to set the absolute zero temperature. So this one, we're using Celsius, so that's minus 273 degrees. And we need to set the Stefan Boltzmann constant, which, because we sketched our geometry in millimeters, should be equal to 5.67 times 10 to the power minus 14. Okay, that's it. Now we should be able to create a job. Yes, let's create a job and let's call it thermal. Okay. Which opens the job window. I just have to press OK. We've now created this job. And let's see if you can write an input file. Let's write input file and give some wording. It says that history output is not requested in the following steps. We can either continue to generate the input file, but there's actually one thing that we have forgotten to do, and that is to make sure that we write out our field outputs. So we've created field outputs over there. It's already created usually, but here we can select what variables we want to write to the output database. So selected are now thermal, nodal temperature. Well, that's the only one we're actually interested in right here. And what we want to select here is state and field. So solution dependent state variables and predefined field variables over here. You can also choose if you want to write it out in every increment, or what I usually do is use evenly spaced time intervals. Let's set this to 100. But well, okay, let's now use every increment. And one important thing to note is that we should set element output position here to average that nodes. This is important because we need to read in these outputs, especially the predefined fields, in the next simulation if we want to calculate residual stresses. And for that we need to write the output at the nodes. So set element output position to average two nodes. Okay. And now let's write the input file. It again complains that we don't have history output, but we don't really need history output. So yes. We have now created an input file of which the name is equal to the job name. So if I go to my text editor, I should see a file here, thermal.imp. There's still one thing that we can do. If we go to the file and look for depth var, Here we specify that we have 12 state-dependent variables in our simulation. But actually, if you use this input file, Abacus is going to output them as SDV1, SDV2, SDV3, etc. So I've provided a small script. It's called thermal input.py, which is a small Python script. It can be run with the Abacus scripting, Python scripting language, which actually inserts some lines into this file to make it the output more readable. So on the top of the file, here you can see how to run it. We should basically use this command and paste that in the command prompt. And then, so it's this command. And then change the file name to thermal.imp. And this should have created a new file which has appended the word mesh to the original input file over there. And if I now look for state-dependent variables, you can see that we have inserted all the variables, which are the same variables that we have in our subroutine, which is the file in this file over there. So there are these ones. That's it. We can now use this file to run the simulation. Finally, we have to create another file specifying some input parameters. The file has to be called setParametersThermal.f90, which will be included in the simulation file. And you can see an example of how it can be set up. So basically, you need to specify the material names over there, and these are the names we have used to for the materials that are specified to our assigned sections. So as you remember, we had two materials over there, base and weld, and we assigned two sections, base and weld, in our geometry with these two materials. And so the names of the materials that are assigned to our geometry need to be specified in the input file over here. So we can set one to base, and one we name weld. These have to be all caps. Actually, if you have only one material, you can basically just do it like this. You don't have to specify its number, but you can if you want to. So you can also set this to 1. Next, here we've specified a lot of the chemical composition parameters of a material. So this is, for example, carbon content, a minimum and maximum grain size. So this is basically if we start austenization, at what grain size will we start? And this is the maximum grain size we can read if we have a lot of grain growth in the model. We don't have to set transformation temperatures, so the subroutine or the simulation calculates transformation temperatures based on formula that are given in literature. But if you want to change those, for example, if you obtain those from thermodynamic software, you can specify them, override the calculated temperatures by the simulation itself. As I've done it here, so all these parameters, because we don't have a number between brackets behind each parameter, and is assigned to all the basic materials in our geometry, so to both the base and the weld. We can do if we, for example, want to have a higher carbon content in the weld. So let's specify that. We can set that parameter C with a 2 behind brackets. Let's set that to 0.3 basically. Then finally, we need to specify a prop file file with properties. This actually now needs to be. So here I need to specify the absolute path to the file with the properties in it. And properties I'm talking about are things like density and thermal conductivity and stuff like that. Note that I'm using a Linux system, so I'm using forward slashes. With Windows, you usually need to use these backward slashes, but it should work the same. But how does that property files look like? I have an example here, a very simple example. And so we basically need to specify 3 properties in this file. The density, the conductivity, and the specific heat. So you can specify each of the properties by starting with a star and then the keywords density or conductivity or specific heat. The second row, this says basically how much entries do we have, so 2 in this case, and these 2 correspond to temperature data points, and then we have 2 rows, and in each row 2 things are specified. One is the property of the ferritic or the BCC materials, so these are ferrite, pearlite, bainite, and martensite properties, and this is the property of austenite at 20 degrees over here, so at this temperature. So basically, if you have a material at 20 degrees temperature, you have a microstructure composed of both ferrite and austenite, it interpolates between these 2 values. Then we have a second row specified for 1500 degrees, so basically meaning that if I have a temperature in between somewhere, it also linearly interpolates between temperatures. And basically the same for the conductivity and specific heat. So this is a very simple input file where we just have 2 data points and we linearly interpolate between that. But here I have a much more complicated, but a longer one with 100 data points per property, which I have obtained from a thermodynamic database. But you can, well, make this list as long as you want. So we've specified that here, and now our simulation should be ready to run. So we can open our command prompt and we can type in abacus. The job name is thermal. The input file equals thermal. And we specify the input file with the inserted state-dependent variables, which is this one. We want to specify our user subroutine, which is called synthermal.f90, and use the word interactive so that it keeps running in the command prompt and it doesn't run in the background. So it's compiling now. And now it should be running the simulation. You can check on the simulation because if you go to like the working directory, you can see the files here. And if you click on the .stuff file, you can actually see where it is in your simulation, how much steps is it on. So if you refresh, it takes a while, but if I refresh this, you see I'm now further in my simulation. So the simulation is finished, so we can now go ahead and open the results file, the ODP file, and see the results. So above here we can select, well, you can select either the field variables, which 1 to 5 are the phase fractions, or you can select the state-dependent variables over here. So this should be the ferrite fraction, like this. So you can see that the base metal has a ferrite pearlite fraction, nothing has changed over there. And probably the weld has mostly become magnetic fraction. Furthermore, you can view the temperature fields. This is at the end of the simulation. It's almost that's gone down. Yeah, you can basically scroll through all the welding steps.